One, two, three. Yeah, it works. Welcome, everyone. Welcome to Python and Bloomberg, an open source duo. We could just have titled this Python and Bloomberg, but like nowadays you need catchy titles for talks, right? We were between Tango and Duo. I was more on the Tango side, but we ended up with this name. I hope you like the talk. Well, we're going to have multiple speakers today. We wanted to use this talk as, we want to do a similar talk every year. We want to use it as a yearly update on what we're doing on Bloomberg, in case you're interested on the open source work that we're doing. Off the clicker. In terms of the agenda, I'll start real quick with what's Bloomberg and how do we use Python and our relationship with the PSF and the Python community. And then we're going to have two main sections. One's going to be an open source update. This is some of the open source work that we do. It's a project we contribute to. Pablo is going to be speaking about the work that he does in CPython as part of his Bloomberg work. Pradyun will be speaking about PEEP and packaging in general. And there are some other Bloomberg employees that contribute to open source. If you see anyone, go and ask them, because contributing to open source, we try to contribute to open source as much as possible. After that first section, we'll speak about some tools. We'll do a spotlight on some of the tools that either are already open source or that we are going to open source. I know many of you here came because you heard Pasty about Memray, and you wish you had known about it better. So this is your opportunity, because we just made yesterday PyStack open source, and Pablo is going to speak about this tool that I know for sure many of you will be using in the future. In terms of what's Bloomberg, well, what you see here is the Bloomberg terminal. It's kind of like the main product. It's basically what many of us work on. It's basically a software that allows you to get any kind of information related to finance. If you haven't seen it before, I would really recommend you. Yes, we're hiring, but that's not what I'm trying to do here. If you haven't seen it before, I recommend that you go to the booth and just try it out. Whether you have any interest on finance or not, there's really cool information that you can see in the terminal. And if you just go through the booth, they can show it to you. With you don't need to apply and anything like that. You can just see how it's being used. This is a tool that's used by many people across the globe, and just getting to see how it works, I think it's quite cool. Aside from the terminal, we also provide things like news, enterprise data, and some other enterprise program. That's kind of like what Bloomberg develops. About Bloomberg, Bloomberg's a technology company that was founded before I was born. I'm not as young as I look like, I promise. If you want, we can speak about that afterwards. But yeah, it was founded in 1981, which is a bit surprising given how we work, because many times it feels like it's a small startup. We have hundreds of thousands of subscribers all around the world, and there are approximately 20,000 employees spread across the globe, and we have 7,000 engineers. Both the company and developers are quite distributed. Actually, the team I work on, we have a person in San Francisco, another one in Athens, multiple people in London, people in New York, and I'm working from Madrid, living the dream. And yeah, if you're interested in traveling through Spain, oh right, Philadelphia. We have a person from Philadelphia. I always include him in New York. Sorry, Matt. Big shout to Philadelphia. He's also living the dream there. If you're interested on any travel trips on Spain, let me know, and I can also help you out with that. But yeah, on Bloomberg, we are trying to contribute more and more to open source. We have been using it for quite a long time. Many open source projects, and we are getting more and more involved with open source. You'll see in a bit. A big part of Bloomberg is philanthropy, and we also take into account contributing back to open source as part of it. We, as we said, like many companies rely on open source just to survive, right? Like open source is now the base of many software companies, and I think it's more than fair to give back. We have increasing presence in academic research. If you are into research, you might have seen some recent papers, especially on the ML area, where Bloomberg is pushing the edge. In terms of Python and Bloomberg, I'm excited to say that developers at Bloomberg are able to use the latest version of Python from day one when it's released. If that doesn't lure you to work in in Bloomberg. I don't know what would, because it makes me so excited. The team I work on works really hard to make sure that that happens. And we are already working on making sure that we can use Python 3.12 as soon as it's released. It's amazing. I don't know how is your experience here at companies, but the company I used to work before, we were like anchored on a 10 years old version of Python, and being able to leverage the latest feature of Python just feels great. We also think that it enables us to better contribute to upstream, because the fact that we're able to use the latest version of Python allow us to, well, also hit some of the issues, but to be able to contribute in a meaningful way. Python is the number one language in number of repositories. Again, if you know Bloomberg, many of you probably know it because it used to be a C++ shop. We have transformed now to a point where Python is the most used language and kind of like the de facto language for any new application. I think that's amazing. There are still many people doing C++ because there are many like time-sensitive software that we need to develop. But if you know Python, now Bloomberg it's an amazing company to work for. We have tens of thousands of Python applications running on our system. We handle a huge volume of data because Bloomberg basically aggregates data from a lot of financial sources and provides to users. So a lot of volume. We have people in the steering council. Pablo, who's here, who's going to present. 2 core developers, multiple committers in PyPA. We were heavily involved in the project Jupyter. You're not going to see anything about that today. We hope to bring someone that's involved in a project that uses Jupyter and contributes upstream next year. And we've been a PSF visionary sponsor from a long time. I'm really you're the first one to hear this. We are going to be sponsoring a deputy developer in residence with the PSF. That means that not only we will contribute with code upstream, but we also want to contribute with money as well. So yeah, we think that many open source projects sometimes don't get the funding that they need. We've been in the past sponsoring the packaging community, and we have raised our commitment, and now we are able to sponsor a deputy developer in residence, something that came from the core dev saying that they need it. We're super excited because this will allow to run some projects that need a person fully committed to a project. As you can imagine, it's super hard to drive a project like Python just based only on volunteer time. I know Pablo here can speak a lot about that and crazy nights. But yeah. So as I was saying, I'm hoping to be able to use this lot every year to give you an update of what have we done in the open source space, what have we contributed that is useful for everyone, so you can use this as a way to know what's coming and to get some kind of condensed updates on what's coming on the Python space that was contributed by our developers. And we'll also be doing some spotlight on the tools that we are open sourcing, or we have open source. So with that, I'm gonna pass it to Pablo. That's how you pronounce it in Spanish, no Pablo, or yeah, and he's gonna speak about his work in CPython.
Thank you. It's quite funny when you go to Starbucks and say Pablo. I have all the possible permutations. Cool. So I'm going to talk about like my work on CPython, in particular what I have done this year. So I'm lucky enough that I kind of convinced my employer Bloomberg to give me some work time to work on CPython. Particularly these days, I'm spending like 50% of my time on it. And I'm going to talk about what we did past year. And this basically was a collaboration with the Microsoft team that you probably know about, the faster CPython. And I'm going to show you some slides that certainly I didn't reuse from a different talk. But it's kind of exciting. So basically what I'm going to show you is the collaborative effort. So this is not things that I have done on myself. It's things that I have done together with the Microsoft team. And that went into 3.11. So it's kind of a sneak peek into how we make Python 3.11 faster. Obviously, because the talk is quite big, I'm not going to go into detail. But I'm super happy to discuss things later if you have questions or if you want me to go into detail. But first, let me introduce the team. So these are most Microsoft employees. So it's Eric Snow, Edith, Brand, Mark Shannon, which is the technical leader, El and Guido, and that guy. Now I'm missing Michael, I think, which is now the team leader of the team at Microsoft, and I think they're still hiring or is going to grow, but I'm not sure. But anyway, so let me show you some of the things that we did on Python 3.11, which are quite cool. So the first one is frozen modules. So the idea of this is that one of the things that we wanted for Python is that Python starts faster, and this is quite important because, like, most people think about like improvements in Python as like raw speed, like your application runs faster, and that's quite important for everyone. But turns out that starting faster is quite important as well. Think about, you have your command line application, and if showing the help of your command line applications takes 2 seconds, it's kind of like a good experience, right? And it's not like, right now the startup time is not really bad, but like compared with other applications that are written in C or Go or whatever, it was quite bad. So we tried to find ways we could make a startup faster. So one of the things we realized is that if you use like some tools like strace to see what is going on when you start. So strace, if you don't know it, is a tool in Linux that it will show you like system calls. So this is like every single time your program goes to the kernel and asks for something, which normally is quite expensive and it takes time. And if you check like here in the top row, I mean, it's quite small, you cannot see it, but it's called new fstat. That basically every time the interpreter, when it starts, goes to the kernel and basically tries to see what is the status of a file, because it's going to read it. And if you check the amount of seconds, it's basically the most expensive call, and it's quite a lot. Basically, what is going on here is that when you start the interpreter needs to load some files. Normally, this is the standard library, right? Some PYC files with the code. Think about, I don't know, the collections module or the regex module or something like that. And this happens every single time the interpreter starts. And it's slow because it needs to touch disk. If you run this thing on a hard drive from the 80s, it's going to take a lot of time, right? And Bloomberg is quite an old company, so no, we run cool hard drives. Anyway, so the idea, Jesus. So the idea is that we thought that we could actually remove those, and the idea is that instead of like letting the interpreter go to the disk and these slow hard drives and read for those, the idea is that we can create an interpreter that already has these files in like statically compiled inside. So when you compile Python, basically you grab this bytecode from this file and you include it inside the interpreter. And if you do the same experiment afterwards, you will see that, well, this system call now is not the first one, it's the second one, and it went from 85 calls to 14. You still need to read some files, but most of them went down. And if you actually check the time, it's almost like, well, I think 1/10 of that. So right now, Python 3.11 starts quite fast just because it has all these modules statically compiled, and we are still looking into ways we can reduce this number. And the idea at the end is like when you run your command line applications, or even, I don't know, even your server, it starts quite fast. So, running applications made in Python feels quite snappy and not like super slow. This is also quite important if you run it in Docker or something like that when you have limited resources, because then this time basically grows like hell. Just because it needs to touch more stuff, or it has less CPU, or the disk is lower, or whatever. Well, anyway, so that's why Python 3.11 starts faster, which is cool. Sorry, this is another thing. These shouldn't say frozen modules, they say like inline calls. Let me show you what is this. So imagine that you have like a bunch of Python calls. In this particular example, we have like, I don't know, foo calls bar calls bath, and then you call time.sleep. So the idea is that CPython, surprise, is implemented in C. That's the C on CPython. It doesn't stand for Gabor. It starts from C, the C language. And it basically, if you check using debug or whatever, what is the C stack, so basically the calls that you do in C to execute this Python call, you're going to see like a bunch of C calls. But the idea is that every one of these calls here basically takes a lot of C calls, in particular all of these over here. So basically the idea is that every time you call a Python function, then you are calling like 1, 2, 3, 4, 5, 6, 7 C functions. And this is quite expensive. Like, these functions don't do much. They basically like pass arguments from one to the other, or maybe they prepare some functions. So basically it's code that is common for several code paths. But the idea is that even if they are small, just preparing these calls is quite expensive, because you need to like prepare registers and things like that, right? And that is quite bad, because this happens every time you call a Python function. And you may notice this, like the more Python functions you call, the more expensive it is. So the idea that we have is that the status right now is that we have this thing called the evaluation loop. So this is the thing that evaluates the Python bytecode. So I mean, if you don't know it, when you write your Python code, there is something that compiles this thing onto bytecode, which is like a set of instructions. And then there is this loop. You can imagine this as a big function that just grabs one bytecode after the other and evaluates. And if you call 3 functions, basically what happens is that you have one of these evaluation loops. And this loop knows about your code object, so this is the code that you're going to execute, and basically has another thing called a frame object, and this basically holds the value of your local variables, right? Like, you have the same function, but some functions have some locals, and in some of these calls, your local maybe have the value of 1, and some other call it has the value of 3, right? So you need to hold those values somewhere, and basically ends on the frame object. So if you call another function, basically you will have another copy of this thing, so you will need to copy a bunch of C functions again, so pay a lot of time, and this will have, again, the 2 things, so the new function that you're calling and another frame object. And you call like another function, you will have another one. So every time you go in one of these evaluation loops, you will pay a lot of time. And this is kind of okay. It has obviously some drawbacks apart from memory, because like this is using the C stack, and the more you use the C stack, the more you like go into a Stack Overflow. That's why you have a recursion limit in Python, among other things. But we say, well, this is kind of bad because, like this is quite expensive, even if these calls are not doing anything. So what we did is that we removed this schema, and we are using the following idea. And the idea is that it's going to be one of these only. So there is going to be one single function that evaluates the bytecode. And let's say you're calling a function. So the idea is that the frame object knows about what the code is executing. That is kind of like normal because, like you need to store this thing somewhere. But the idea is that if you call a new function, instead of spawning one of these loops, so you call like 7 C functions again to just get, so to grab like a new copy of this, well, we are going to basically link this there. So instead of like calling a new function, what we do is changing the local variables of this function just to point to the new object. And it's the same function, it's just the same while loop. It's just that we change the code that is being executed on the frame. Obviously, I'm making it sound very easy. This was months of work just to get this arrow here. But it's the magic of slides. Very easy, very easy. Anyone could do it. And then you call a third function, then you get another arrow. And let me not even talk about how exceptions work here. But let's imagine that they don't exist. But the idea here is that you can see instead of like having 3 of these guys, we have only 1. And basically, instead of like calling new functions and creating new versions of this guy, we basically link the data. So this is the old trick of changing the data instead of having a function. If you have ever have a recursive function and transform it into iterative functions, it would be a for loop, right? Like factorial. Instead of calling factorial again and again and again, you do it in a while loop, quite classic. You have done any coding interviews at Bloomberg or other companies, then you will know the trick. But it's just like a trick that is 600 times harder because the interpreter is quite old and it's harder. But the idea is that this makes the interpreter quite fast. Actually, depending on your use case, it may be like 200 times faster. Obviously, that only happens when you have a super recursive function and your only cost is calling functions. But in general, I think it makes it like around 7% faster on average, which is quite cool. It depends on your workload, obviously, but the idea is quite simple, as you can see. We call this inline functions, which is kind of like not really what's going on, but we think the name is cool. That's what matters. This is something that Mark Shannon worked a lot. It's called quickening, and it's quite cool. Let me show you the idea here. So imagine that you have this function, like foo of x and y, and then you add x and y. So the idea, like the course of Python is that when you have this function, Python it doesn't know what you're adding here, right? Like it could be strings, it could be like elephants, I don't know, who knows. So the idea is that when you say, okay, Python, like kind of show me what's going on in this function, you will see the bytecode, so the instructions that are going to be executed, and you will see that it's quite simple. It will have 2 load fast. This is basically loading x and y into the stack, and it has this binary op and return value. Obviously, because we don't know what's going on in that plus, this binary op could be anything. Literally, it could be the whole cost of the addition, and I don't know, you could even go to databases in that add. Please don't do that. But it can be quite expensive. And normally sane programmers, I mean, just by yourself if you are one of those, but normally they pass the same values to the same function, right? I mean, maybe you use this function to add strings and numbers because why not? But normally you pass only strings or only numbers because it will have a better name than just foo, right? And the idea is that with Python 3.11, Python will notice if you are passing all the time the same values. Let's say you are passing integers. It will basically mutate the bytecode on the fly. So basically, instead of having those 2 load fast and then the generic binary add, you will notice that you're passing only integers, and it will basically create this adaptive bytecode. And here, like, there is a bunch of changes. So for instance, you have now this load fast. So the idea here is that instead of like loading one variable and then loading the other, it loads both in the same instruction and then it skips over the next one. The reason there is like still a load fast is because we cannot change the number of instructions. Like the code cannot change the number of instructions. What we do is that basically we put both load fast into the first one and then we skip over the next, which looks a bit confusing, but that's life. And then if you check like the and then you check the binary addition, now it's called binary op add integer, and that basically, as you can imagine, rocket science, it adds integers because it knows that you are adding integers. It does a bit more. Basically, it checks that you're still passing integers because you may be deciding that you now suddenly are passing floats or something. If you do that, it will de-optimize. It will learn that you're passing floats, and it will change to binary op add float. But the idea here is that because this knows that these are integers, they don't need to figure out what are those things, and they don't need to figure out like using a lot of C code what to do, and it will run faster, and it will still work if you start passing some other stuff, right? And the idea is that when that happens, if you start passing something else, it will change to this called binary op adaptive, and this is the instruction that is basically learning. So basically, the way this works is that first it will go to the adaptive version, it will learn that you're passing integers, and it will optimize to integers or floats or something else. We have a bunch of those, so it will not, like if you're passing NumPy arrays, it will not basically change to binary add NumPy array because we have only a certain amount of types. But in general, like for types that are built in, we cover mostly all the important ones, and we keep adding. We plan to keep adding versions of this in Python 3.12 and beyond. Well, this is the version with floats, and that's it. And the idea is that you have a bunch of these operations that are adaptive. So here, for instance, this is like a chunk for the what's new on Python 3.11, and you can see that all these operations, so additions, like subscripts, like assignments, etc. So all of these operations learn about the types that you're passing, and the idea is that they will compile into a more specific and specialized version as this is running. And this is the ones that we have in Python 3.11 and how much faster it makes the operation itself. But we plan to keep adding these things because we already have kind of the framework to do it. So there is more. Obviously, this is just some of them that I am very excited about and that I collaborated in some way or form. But let me show you kind of the results. So for instance, this is kind of a public benchmark that we have in the in the speed.python.org website. Sorry, when we track kind of the speed. This particular is a Bloomberg application, by the way, which the data is obviously like is real, but it's salted. But the theory is that you can see that more or less it goes like 20% faster just by using Python 3.11, and you can see like from I don't know, like what is this, like March or something, like how it went faster and faster as we added new optimizations. Sometimes we screw up, as you can see here, but we are not going to let's call it outliers, right? It's not that we did something wrong. Right, certainly not me. Anyway, so it got faster. This is just a Bloomberg application, so it was great for us. But like here are the rest of the Python benchmarks that we measure at the time. And as you can see that in general, some of them got like even twice as fast. But if you see actually the slower one, it got like 6% faster. So if your slow benchmark got 6% faster, like you probably deserve a raise, right? So hear that out. Anyway, so Python 3.11, quite cool. Really great improvements. It got quite faster. Please use Python 3.11. It's a super cool interpreter. I'm certainly not saying this thing only because I also the release manager of 3.11. But like we collaborated and we are quite happy with the improvements, and I'm looking forward to keep working on Python 3.12 and following. And that's everything I want to say for CPython. Obviously, if you want to talk more, I'm super happy to do afterwards, but I'm going to pass this to Pradyun, which is going to talk about pip.
Let's see if the clicker works. It does. Hello, I'm Pradyun. I wear many hats in open source spaces, but relevant to the next few minutes, I am a maintainer of pip. And well, today I'm specifically going to talk about some of the cool things I've done in and around Python packaging that were a part of my day job, effectively. I think most of the audience in the room knows what pip is. It's one of the tools in the ecosystem that basically everybody has used, indirectly or directly, probably directly. And the fact that nearly everyone who uses Python uses pip is precisely why it's particularly valuable to make improvements to it. Like making the error messages just better, making it easier to understand what's happening when things go wrong, and making it nicer to look at. It's nice to not get a wall of red text, especially when the alternative is a structured error that is easier to read, provides more context and guidance. Yeah, that's readable. And this is a significantly better error message. And these are the sorts of things that I've worked on. And it's a big piece of making that happen is that I was doing this as my day job. This is another giant wall of red that is, no longer a wall of red, and explains in better detail what was happening. And it's easier to understand, well, what went wrong, what happened, and so on. These colorful error messages aren't the only thing I worked on. One of the lowest level pieces in the ecosystem is the parser for requirements, which are the things you write within the requirements files. Names are great. It didn't print nice error messages, as is probably self-evident there. And they've been really difficult to diagnose, because the syntax is always slightly tricky. And here's a preview of what's coming in a version of pip later this year. It's the same input as the last call, but now the error has more context, and it's pointing exactly what went wrong and why, and it's clearly stating what was expected. Generally, it's easier to understand. And there's more where that came from. This is my excuse to showcase a few of the cool ones that I found fun to work on. What enabled these was basically a parser rewrite, which actually happened as a contribution to the project that then needed to be picked up and driven to a completion. Well, open source. And the rewrite helped in more than one ways. It removed a dependency in a foundational package, and the whole process is a lot faster. Turns out there was a lot of low-hanging fruit, and taking a closer look at things that have been there since before I started using Python helps make it easier to look at what can be faster. And it isn't just that as well. There's other pieces around Python Python's packaging tooling that have gotten quicker. Pip, for example, has gotten much quicker at certain parts of building your projects. This screenshot is probably my favorite PR out of the bunch, which utilized some import lib magic, and now local package installations are much quicker. The number is from a random test on my MacBook Air, 6 to 7 seconds outside of pip's control, and it's a 12-second build, and now that shaves 3 seconds off of that. This improvement is visible for most builds, and it's especially drastic for things that involve NFS. One of the pieces that I'm most excited about that's actually just been released like a couple of days ago as we were coming to PyCon is a significant improvement in pip's dependency resolver, where it's just ridiculously better. It started again as a contribution from someone in the community, and there's just been a lot of discussion around how do we make this happen, and lots of people providing input into that. And well, this had multiple pieces in trying to go from, okay, this is theoretically what we can do, to actually having it implemented, rolled out, and all of those fun pieces. And all of that is made easier by being able to sit and work on it for a whole bunch of time. With that, I'm going to hand it over to Laszlo to talk about shrink wrap.
Hi, everyone. I'm going to talk about shrink wrap, which is a packaging tool which powers literally thousands and thousands of application deployments in Bloomberg. In this talk, I'm going to talk a little bit about what is shrink wrap and why we felt the need to build something like this, a bit about the motivation, a little bit about how it works, really high level, and I want to showcase some of the sort of open source integrations and some of the tools we're using and leveraging in shrink wrap. So first of all, what is shrink wrap? It's a self-contained application bundler. There are other similar tools. What these tools tend to do is that they take everything which belongs to your application, including the application code, your dependencies, and the Python interpreter itself as well. I think this is slightly unique to shrink wrap. It takes all of these and creates an independent bundle, which then you can deploy to a machine which doesn't even have to have Python installed. So it basically pretty much decouples the runtime environment from your deployment environment. from your build environment. This enables rapid deployments. It enables you to upgrade Python and your dependencies whenever you want, very quickly, very rapidly. This tool at the moment is supported on Linux, Solaris, and AIX. Yeah, we use those platforms. It also works on macOS, but that's not a supported deployment platform in Bloomberg. To better understand why we built shrinkwrap, I think it makes sense to talk a little bit about the past, how things worked before shrinkwrap existed. So in general, packaging and deployment in Bloomberg for all application or all languages work through a semi-proprietary packaging standard. You can imagine something like a trunk-based development model where you have packages for C++, for Node.js, for Python. They will have generally one version at any given time of each of your packages you want to use, and then you would deploy these on a system-wide deployment. This means that you usually can only have a single version of a package installed on any given machine at any given time. That means that all the applications on that machine, and pretty much across all of the machines, will share that single version of dependency, which is a significant drawback of this model, especially for something like Python. This works really well for something like C++ when you build everything statically. Then you don't really worry about this much, and especially if you don't have a lot of external dependencies. But for something like Python, where we really want to leverage this entire massive ecosystem on PyPI, it becomes an issue. This also means that dependency upgrades can become complicated, because now you upgrade something like, I don't know, NumPy, you upgrade it to a new version, and it might affect a lot of applications, which you don't want. This can slow down adoption of newer versions of packages. It also means that every single Python package needs to be repackaged for this custom, fairly semi-proprietary packaging standard, which again can inhibit adoption of newer versions and new sort of PyPI packages. And lastly, it requires some amount of custom tooling in the development process. It can mean that you wouldn't be able to necessarily use something like virtualenv or pip or whatever is the latest and greatest open source tool you can plug into your development process, because you need some proprietary tooling in the place. How things are now with shrinkwrap, how things have changed is that now developers can freely pick whatever dependency version they want. It will only affect their application because everything is self-contained. So they can easily perform package upgrades because it only affects their application. They can do this without impacting any other application. They can easily roll out and back out these applications whenever they want without impacting any other applications. And they can now leverage PyPI packages, basically use any standard OSS Python tooling, pip, virtualenv, whatever they really want, because this all leverages standard Python packaging standards, and you can just use PyPI packages. So a little bit really high-level overview of what shrinkwrap is or how it works. The blue rectangle is shrinkwrap there. So it takes source code and configuration. The configuration is PyProjected TOML. You feed this into shrinkwrap. It will install the declared dependencies. This is one of the distinguishing features and the reason why we didn't go with something like PyInstaller, because we wanted a completely declared sort of and dependent installation model where you can say, these are the things I need and these are the things I want to bundle. So it will install all these declared dependencies using pip into a staging environment, which is basically just virtualenv. And then it will start bundling all the library dependencies, your application code, the Python interpreter, all the native dependencies as well. So you can have extensions, you can have native extensions in your application. It will create custom hooks, runtime hooks. This is needed for certain things. For example, you don't want to use a certificate bundle shipped with your some random PyPI package, because that can go out of date once you deploy that, or time zone databases. We always want to use those things from the machines because we know that those machines will always have the canonical correct version of these things. And finally, it generates launcher scripts, which will ensure that whatever script you launch your application through will use the bundled interpreter and not something else on the machine, a different version of the interpreter. And then finally, this just creates an output bundle. It's really just a directory containing all of these dependencies and your application and the interpreter. And you can take that bundle, copy it to any machine you want. It only requires a minimum set of packages from the operating system and facilities, and then it should work. A few words about some of the open source tools we're using in shrink-wrap. Obviously, pip, as I mentioned earlier, we use that to install these dependencies. We use virtualenv as the staging environment where we're installing these packages. We have a custom dependency resolver based on resolvelib. This is necessary because we do offer integration between PyPI and our custom internal packaging format, so users can use that if they want, and just to make it possible to integrate these two and have two different package sources work together, we have a custom resolver. We use PyElf tools to inspect ELF binaries and use patchelf to do dark magic with these ELF files to relocate things, and we are patching ELF files. We use different mechanism on Solaris and AX where these wouldn't work. Yeah. And I think it's important to mention or highlight here that we either employ maintainers for almost all of these projects, or at least we have significant contributions in these projects. And lastly, if you own a similar tool, or you use a similar tool, or you have a similar problem, but you don't have a good tool to solve this problem, we would love to hear from you. Either catch us on this on PyCon, or just shoot an email to one of these email addresses. We'd really love to hear from other folks and their experiences. There might be an open source feature for shrink-wrap as well. Who knows? But we'd really love to hear from you. And with that, I'm going to hand it to Matt to talk about the most amazing Python memory profiler ever, Memory.
All right, so yeah, I'm going to talk about Memory. I am one of the maintainers, although I think everyone you've heard talking today has contributed something to Memory over time. Pretty major contributions from everyone. I'm one of the current maintainers, though. As Laszlo said, it's a memory profiler. So what is a memory profiler? It's a debugging tool that lets you figure out where your process is spending all of its memory. That tends to be a major concern that people have when they have a deployed application that turns out to be using much more memory than they expected, and they need to track down exactly why that's happening. So what Memory does is for every allocation, it tracks the stack where that allocation happened at, the thread it happened on, the size of that allocation, the allocator that was used to make that allocation, and then when that allocation went on to be freed, and if it went on to be freed. Given that, we're able to show you the full path to where that allocation happened from the Python functions that were called, right through any C functions that were called. So you can see here that this is an allocation happening inside of NumPy. We're able to show you the full stack to that with the Python frame showing in green and the C frame showing there in gray. One cool thing that we do is we output one kind of capture file that can be then used to generate multiple kinds of reports. So here you see us generating a statistics report that's showing you a histogram of allocations by size. We have a table of just all of the allocations that were performed while tracking was active. We can show a tree showing where the biggest allocations that the process made occurred. We can show a flame graph that identifies the different allocations broken out by the size that they are, as well as the ability to switch between threads and show what different threads we're doing at different times, and even a live view that is able to update as the program is running and tell you where the program is currently spending its memory as it runs. So we also, over the last year since we released this in last April, so right before PyCon 2022. Since then, one of the major features that we released is a tracking API that lets you integrate directly in your code the ability to turn on memory tracking, start capturing data, and turn it off when you exit a context manager. We also have integration with PyTest that is able to tell you which of your tests is allocating the most memory, what functions in those tests are performing the largest allocations. You can see this is enabled by just passing the --memory option to your PyTest call while the PyTest memory plugin is installed. We also have the ability to limit the amount of memory being used by any of your tests. So you can say this test should never use more than 24 megabytes of memory. If it does, I would like the test to fail. And the plugin can do that for you. One feature that we've built since then is that for this marker to work, you no longer need to provide the --memory command line argument. You used to need to provide that. Now you get that for free whenever pytest.mark.limitMemory is used. So let's see. The other thing I want to talk about is what has changed in the last year since we originally released this. I didn't make slides for all of these things, so I'm just going to run through a whole bullet list for you. Sorry. One of the biggest complaints we got from actual users once we released this is that the environment they were testing in often involved long-running processes where they weren't able to isolate the part of the program that was interesting and figure out where they wanted to dive into. So they just ran memory across an entire hour-long run of a I don't know, say NLP job or something. And they found that the capture files that we generated when you left memory running for an hour were enormous. So since our initial release, our capture files have been reduced and reduced and reduced in size. We're now down to about 98% smaller for the same amount of data than our original release had. Our flame graphs now are, the HTML that we pop out for our flame graphs is now about 85% smaller than it used to be. We have compression of all of our capture files by default now, so we automatically compress everything that we output in order to shrink it even further. And we have just a brand new feature, actually, as of maybe 2 months ago, the ability to get an aggregated capture file where instead of dumping all of the raw data for every allocation that occurred, we summarize it by the location that it occurred at and just dump that to the capture file. There's a couple of types of reports that won't work with, but for all of our most common reports, that gets you the information that you need to generate like a flame graph of the high watermark usage of the process or a flame graph of what leaks occurred from the process. It can get you all of that using drastically smaller capture files. Again, something like 95% smaller than our already 98% smaller capture files. It's ridiculous how much we managed to squeeze into those. We now have a Jupyter magic that you can use to profile a cell in Jupyter or in IPython. We've got a new type of report that captures temporary allocations. So it's designed to help you figure out if your program is allocating memory and then very quickly after it allocates it, removing it. You see this happen in places where, say, a list is being appended to over and over and over and over. The way a list works in Python is that it is a dynamic array, so it resizes to every time you need to add a new element to an array, it checks if there's already capacity to add that, and if there's not, it allocates a new larger array under the hood and starts filling that in with it copies over all of the existing data from your list and then adds your new item to it. That allocation pattern means that if you're repeatedly appending to a list, you wind up repeatedly copying over all of the beginning elements of the list and then copying them into a larger array over and over and over. And that can be really inefficient. Our temporary allocations mode can help you figure out when you're doing that by figuring out when you have allocated something and then just immediately throw it away in favor of another larger thing or something like that. We have the ability to attach to a running process now. You can ask us to inject ourselves into some process that's already running and start capturing the allocations that it performs from that point forward. PyTest memory lets you preserve the capture files that it records. So in addition to giving you a report, you can ask it to save the capture files so that you can investigate them yourself after the fact. We have support for debug info D now. So if you are running in a distro where they don't ship debugging symbols for their interpreters or something like that, you may be able to download debugging symbols on the fly. Memory integrates with that and is able to fetch all of those symbols for the C calls, even if your interpreter doesn't have symbols built in. We can hide frames for imports that are happening in the flame graphs, which lets us generate much cleaner looking flame graphs. And we built a ton of new features. Probably the biggest is support for Mac OS. When we released it, we only had support for Linux. Mac OS is a huge new feature. Support for 3.11 turned out to be surprisingly involved because of the... Thanks, Pablo. Because of things like the inlining that Pablo talked about, the fact that now we no longer can map just one Python function call to one C call, it turned out to be surprisingly difficult to integrate with that. We support muscle libc now, which you might not think is a big deal, but again, turned out to be way more difficult under the hood than you might expect. We have some amount of support for greenlit, so if you are using something like gevent and you have multiple threads of execution that aren't really separate operating system threads, we can tell you what's happening in each of those. We support tracing the Python allocators as well now. Previously, we only really traced the C-level allocators, and we could tell you the Python stack that led to a call to malloc happening under the hood. But now we're able to give you the stack up to a point where data or space is requested from one of the Python memory pools. Under the hood, Python pools memory for efficiency. And it only refills those pools using malloc when it needs more space than is available, or if you're trying to allocate something so large that it thinks that it's not worth pooling. We're now able to, at the expense of extra time spent tracking and larger capture files, we're able to tell you every time any Python object gets allocated, basically, instead of just the point at which the system gets asked to give more memory to Python using malloc. Let's see, that's almost everything. We've got a couple of little small things. We've got the -C command line argument to memory run that lets you profile a single command. That was something that someone asked for. And we've got progress bars now is a huge one. One of the problems with our giant capture files that we used to have is that you didn't get any transparency into what was happening while memory was chugging along and trying to produce a report. And now you get at least some information about what's happening and how long it's going to take, which is hugely helpful. And coming up very soon, we have PRs in flight. One has landed and one is still underway to try to get the ability to do temporal allocation reports. So one of the things that's really unique about memory compared to other memory profilers is we capture a tremendous amount of information, much more than what other memory profilers capture. We have the ability to tell you where things happened in time. So we can show you, well, we can't today show you, but we soon will be able to show you something like if you, backing up a little, one of the types of reports that we have tells you what the high watermark is from your entire run of your process, like at what point your process had the most memory allocated. One of the reports that we have is the ability to tell you what was leaked from your process, so anything that was allocated and not freed. We have a ton more information than that, and we've never really figured out a good way to show it, and we think we have now. So we're going to give you the ability to select a range of time and figure out what the high watermark point between 2 points is on your flame graph. Or the ability to select a range of time and tell you what was allocated within that time window and not freed by the end of that time window, which lets you sort of drill down into your process as it's running, and you can recognize, okay, there was this big peak of memory, and at that point we know that we've finished all of our setup and we've imported everything that we're importing, and we have built the arrays that we're going to work with for the rest of our process. But then there's this other little peak over here, and I want to know what caused that little peak. We're going to give you the ability to sort of drill down into that specific area and figure out what was happening there, coming very soon. And I think that's all I have to say about memory. So I'm going to hand it over to, I think this is Pablo. Is it Pablo?
Hey, what's up? This is Pablo. Cool. So that's the last thing. So just hang with me a bit. So I'm going to present the new cool stuff. It's called PyStack, and it has this cool logo because it's like a stack of pancakes. And we have pancakes actually as merchandising. So you can go to the Bloomberg booth and have pancakes with the logo, which is it's quite wild that you make like a program and then this ends in pancakes. Kind of a life-changing event. Anyway, let me talk about this. So imagine kind of like this, figure this out, right? Like you're a Bloomberg employee, so this is why this was created. You're a Bloomberg employee, it's 9 a.m., you come to work or something, if you come at 9 a.m., which probably you don't, but like, you know, figure it out. And then you see that there is a bug report, and it's because like one Python application that has like insane amount of C extensions and whatnot, it just crashed. And because you know you work in a large company, we create core files, right? Because it crashes, it's segfaults, something underneath segfaults, and you have a core file. And now you know like everything is red and the world is burning, and it's your task to solve the problem, right? And then you say, okay, let me attach a problem. So let's say this is your application. It's a super enterprise ready sleep, 1,000. Yeah, it creates a lot of money. This thing. So you know it crashes. Because you know who knows what happened. Maybe the sleep is hardcore sleeping, and then you attach a debugger, right? And what can you attach to a core file? Well, you can attach GDB, for instance, and it gives you this, which is kind of like a lot of C code, and it's not very useful, right? And then you cry on a corner. That's the situation. That was bad. We don't like our developers to cry. I mean, we respect that. We are a very inclusive company, but we recognize that this is not useful. Why is not useful? Well, because like every one of these functions actually is mapped by, as you saw before, any one of like 6 or 7 of these things. And what is worse, when you see this thing on GDB, it doesn't tell you which one it is. So you are only seeing this code, and you don't know like actually that what's happening is that you're calling sleep, and then you're calling this function, and you're calling this function. So basically, the technical term for this, I think it appears on several of notebooks, is called useless. It's useless. Computer science for you. Anyway, so what PyStack does, so instead of using GDB, you use PyStack, almost the same invocation, PyStack minus C the core, and then you get this. Wow, incredible. It works also even if you don't have the Python binary around, because like we do a bunch of dark magic and whatnot. That was certainly not insane to code. But yeah, the idea is that you get this, and you get the Python stack from the core files, but you can also get them from Python processes. So imagine that instead of like this scenario that I just described to you when the process crashes and then you need to analyze the core file, imagine that what happens is that you have a Python process that is stuck, is just hung. You don't know what is going on, or maybe it's just too slow. So you can use PyStack as well over that process, and you can attach to it from the outside and say, well, PyStack, tell me what this process is doing. And basically it will print you this. It will say, well, this process is kind of sleeping, and basically this function is calling this function, is calling this function, which is quite cool. But what is cooler about this is, like, you know, as I described before, it turns out that in our imaginary story is certainly not real. Like normally you don't use just Python, you use a lot of C and C++ and Rust and whatnot. And that is kind of important, right? Because like if you have some complicated, for instance, machine learning applications, what you're going to have is not just this super simple enterprise-ready code. What you're going to have is Python calling back into the C++, etc., right? And this is quite hardcore, and the thing gets super, super messy when you have like several levels of this. So sometimes this is actually not useful, because like maybe between these two calls there is like some C++ code, and maybe you are a Python-only developer and that tells you nothing. But most of the time you are you know a bit of C or C++, or maybe you are even using the library, or you are creating a bug report, and those C and C++ calls actually tells you a lot. So one of the things that you can do with PyStack as well is that you can transform this madness into, you remove those calls, and then you can transform it into that madness. So you can see here that, like there is a function, a bunch of C functions, and then you go into your Python functions, and then you again into your C functions. So we call this the hybrid stack. And the idea here is that you can see how Python and C++ intertwine, and you can see like some Python called C++. You can see here, like, let me show you one of these reports a bit better. So you can see here that, for instance, you see that the program starts on start, and that calls like start main and a bunch of like Python functions. So you have the C here, which is C code, and then it goes into your first Python function, which is first function. It goes into a bunch of more C Python functions, etc. Third function, the sleep call, and you can actually see that that sleep call doesn't end there. What happens is that it goes into libc, and you can see that calls like into the time module in Python, and finally it goes into select. Surprise! When you call sleep on Python, you're actually doing a network call. What about that? Well, it's not a network call, but it's using the select primitive to sleep because it wants to be interruptible by Control C. Now you know something. It's not calling a sleep underneath. It's called select. So you can know that by using PyStack. How cool is that? Huh? Now you're supposed to clap. Awesome. So yeah, this is kind of the thing. It doesn't do as many things as memory, but this is kind of cool enough and it's difficult enough to maintain because it needs to know about all the versions of all the interpreters and all of that thing. We support like all of them. We support even Python 3.11. Actually, one cool thing about Python 3.11 is that when it shows you these things, because of the work that I did in Python 3.11 with the cool error reporting that basically tells you not only the line where the error happens, but also the columns, we also highlight that information here. So we show you exactly like what part of the function call the program is running. So, I mean, there is a bunch of things that I'm not going to read here, but the idea is that that's what it is. It's basically a program that is attached to a core file or a process and shows you the stack of what's going on. And the main idea compared to other programs that do similar things, because like this is not just new in the Python ecosystem, you have other things that can do similar things like PySpy and Austin and things like that, normally profilers, but this is a debugger. And the idea of a debugger is that it puts a huge amount of effort of giving you the information at the cost of being a bit slow because you're not the profiling your program. You want to know what's going on. And also it works on core file, which none of the profilers do at the time. So the idea is that, for instance, when you have a core file, even if you don't have the Python executable or even if you don't have the libraries, we're able to still show you most of the time the Python stack. And this works even if you move the core file to a different machine. So think about that, I don't know, some client sends you the core file and say like, hey man, figure this out. And you can use secretly this cool tool while you are eating a pancake. So that's it, that's PyStack. You can learn more about in Bloomberg PyStack and you can like start the thing if you want. And we plan to add super exciting new features. And you can also help us with our booth and grab a free pancake, I think, which is there cool and get you the logo as well. I think that's everything we have here. So thank you very much for coming. We're super excited to have you here. And any of us are super happy to talk about our open source involvement or Bloomberg, if you are interested on Bloomberg. But yeah, that's all. Thank you very much for coming and see you around.